Hi, pre-calculus friends. Here we are in chapter 2, and what we're going to do is talk about modeling real-world data with matrices in section 2.3. Our vocabulary is a bit extensive, to be quite honest, so I'd like you to kind of hold on and prepare for a longer video. So these are examples of different matrices, the plural for matrix, and a matrix is really just an array of numbers. And that's something that I know you've seen before, but it's always a thing that we don't use in daily life. So it's kind of like, oh, here this thing comes up again. But matrices can be very powerful, and so we're going to talk about them in this chapter. So matrix is what you see here. You see several matrices, and inside each matrix, it has elements. So each of these numbers inside of the matrix would be considered the elements. Now, when we talk about a matrix, we have to talk about its size. The m by n matrix refers to the number of rows by the number of columns. And so in this case right here, we are looking at a 2 by 3 matrix. Over here, we have a 3 by 3 matrix. Here we have a 1 by 4, and here we have a 3 by 1. The dimensions of the matrix is how we are describing them when we put this 1 by 3, 3 by 4, and all of that stuff. So let me kind of highlight that so we can see the relationship. So another way of talking about the dimension is to talk about the m by n-ness of the matrix. So we can have a row matrix and we can have a column matrix. And you can see that that is expressed here. We have a row matrix where our matrix is just a row, and a column matrix where our matrix is just a column. And then we can have a square matrix where the width and the length, or the row and the column, agrees. So our square matrix will highlight in this funky green color here. Would be this guy over here. All of this would be our square matrix. Okay, that's not too bad. We're getting through this. When we talk about an nth order matrix, this is always also another term for a square matrix. So in this case, the nth order matrix that we're dealing with would be a third order matrix because it is a 3 by 3. I hope that kind of makes sense. So these first few terms, hopefully they're feeling okay. Let's go on and get to the next bunch. So it should be clear what equal matrices are. So if you have equal matrices, they have to have two things going for it. One, every element in both of the matrices must be organized exactly the same way, and it must be of the same size, right? So if you have equal matrices, basically A, B, C, D, you would need it to be exactly the same. So that's what equality is in matrices. I hope that makes sense. So those are equal matrices there, exactly the same. A zero matrix, on the other hand, is a bit different. So the zero matrix is a matrix where all of the elements are zero, and shape in this case does not matter in the same way. So you could have an n by n zero matrix, or you could have a zero matrix that is not n by n, that is n by m, meaning the column and the rows are different. So a zero matrix is a matrix where all the elements are zero inside of the matrix rather. All right. So we've got the additive oh no, did we do addition of matrices? I skipped it, sorry babies. Addition of matrices. So equal matrices, we got that. Zero matrices, we got that. Addition of matrices is really just addition, but when we do it, let me show you. Okay, so addition, my bad about that. Addition matrices is that when you're adding matrices, you need to make sure that they're exactly the same size. They don't necessarily have to be a square matrix, but they have to be exactly the same size. So you're adding element for element, and you're going to get a same size result. So you would add in the same places. 1 and 3 give me 4, 2 and 7 give me 9, 3 and 5, 8, and 4 and 1 would give me 5. So this would be the result of addition of matrices. The additive identity matrix would be the same as if we are having the additive, not the additive inverse, but if we're adding and we want the additive identity, basically it would be a zero matrix of the same size. So, for instance, if I wanted the additive identity to this matrix here, this 1, 2, 3, 4 matrix, it would just be, in this case, a square matrix that is a zero matrix. So that's the additive identity, because when I add it, I'll get the same thing back, the original matrix. So additive identity, subtraction of matrices, very similar to addition of matrices, except you're subtracting, the same thing applies. You definitely need to have the same exact sizes. And so we are really subtracting element for element. So if I were to subtract these two matrices, I've just changed that to subtraction, it would be 1 minus it. Well, it would be, let's change this one so it's a little bit, I know I don't need to do this. You guys know what I'm talking about. Let's change it so it's not the zero matrix. So 1 minus 2 gives me a negative 1. And then everything else would be the same because I left it that way. And so this would be the result. You can see it kind of in the corner. All right. Hopefully that's making sense. So we've got additive identity matrix, a subtraction of matrix. Now scalar. I'm going to clean off this space so you guys can see a little bit more. You copied the notes. I know you got it. Okay, so scalar. The next thing is when you have a matrix and you are simply multiplying it by a number and it'll be on the outside, and that's called the scalar. So let's do EF, and let's say G is out here. So when you multiply a matrix by a scalar, each element of the matrix will be multiplied by that scalar value on the outside, right? And so this is a lot like distributive property, actually. And so that's what our result would be. And so the harder the scalar product would be the result. So this would be the scalar product. This guy out here is the scalar. And here we've got the product of two matrices, which requires attention to the size of the matrix. You got to be really focused on what the size is. So what we realize is that when you're multiplying the product of two matrices, when you're actually multiplying the matrices themselves, you need to make sure that the column of the first one is going to be equal to the row of the second one. So an M by N matrix multiplied by an N by R matrix in terms of size will result in an M by R matrix. And I'm going to save this visual for the example so we don't spend a whole lot of time. But this is going to be very necessary when we are multiplying our matrices. Let's go check out some examples. So our first example is pretty straightforward, where we're going to basically take some information and place it in a matrix, and I'll do that right here. And so we're just talking about the prices of different items depending on the location in which you buy them. And so since we're dealing with 3 items and 4 different locations and the prices corresponding to each, we're going to make a matrix, and it'll look a little bit like this. So here's our matrix of the information displayed in an organized way. And, you know, this is cool, not super hard to do. So that's the first part of the question. The next thing that we're asked to do is to use a symbol to represent the price of pain reliever in Mexico City. So we see the pain reliever is here, Mexico City is here. And so what we want to do here is talk about the element. So if I called all of the elements A, but now I need to consider where its location is. So the location is at row 2, column 3. And so I'm going to put A23 here to represent that specific location. Here we are at example 2, and we're going to find the values of x and y given this matrix equation. So what we're seeing here is that this thing is equal to this thing. If these two matrices are equal, then the elements in each place would be equivalent as well. So you would end up with y is equal to 2x minus 6, and x is equal to 2y. And so with this, we can do all kinds of things. I think substitution looks really easy here since x is isolated. And so we're going to plug the x value right there, the x value being 2y, right into the equation for x. And when we do that, we get the following: y is equal to 4y minus 6. Moving the 4y over to the other side, we end up with negative 3y is equal to a negative 6, and therefore y is equal to 2. If y is equal to 2, we go back, we plug it in, and we know that x is equal to 4. So the values are x equals 4 and y equals 2. Addition we talked about earlier, so this example shouldn't be too hard. If I'm adding a plus b, I know that I need to add so that the shape is preserved of each of the matrices, and they have to be exactly the same shape. And so you can probably do this with me. Negative 2 plus negative 6 is going to give me negative 8. Then 0 plus 7 gives me the 7. 1 plus negative 1 is 0. 1 plus 0 plus 4 is 4. 5 plus negative 3 is 2, and negative 8 plus 10 is 2 as well. Subtraction is going to operate similarly, so we know we have the same exact shape, and we're going to just subtract element for element. 9 minus 8 is going to give us 1. 4 minus a minus 2 gives us 6. Negative 1 minus 6 gives us 5. 3 minus 1 gives us 2, and 0 minus 5 gives us negative 5, with negative 4 minus a negative 5 giving us a positive 1. So here we have a little bit of scalar multiplication where we're given a matrix and then we're asked to find 3 times that matrix. And so this is where we talked about having to kind of use a distributive property mindset where we're going to distribute the 3 outside of the matrix to each of the elements inside. And instead of recopying it, I'm really just going to give us show the result of that multiplication. And I know you guys can do this, but just do it with me. Let's have fun. 3 times negative 4 gives me a negative 12. 3 times 3 is 9. 3 times negative 3 is a negative 9. So we've done the first column, and we'll go on to the second, where we get 3, 27, negative 3. And here in the final column, we get negative 3, 0, and 24. And so that kind of fell out of there. Let me make sure it's all fitting. Is the result of scalar multiplication on that matrix. So here we're dealing with scalar multiplication, and order does matter. So doing a times b would be different than b times a, and that's something that you may remember from a previous course. But let's take a look at multiplying a times b. So since order matters, I'm literally going to line everything up exactly as the order indicates, a first, then b, and I'm going to rewrite the matrices. And you remember we talked about having to make sure that the sizes are the same or are corresponding, particularly that the column matches the number of rows. The columns in the first matrix matches the number of rows in the second matrix. And that is really specific. The 7 and the 0 times the 3 and the 5 added up to get the first element of the product. So it gets a little bit involved. Let me make this a little bit larger. So 7 times 3 is 21, and 0 times 5 is 0. So I'm going to add those two together to get the first element of my result. Next, to get the element underneath there, I'm going to do the same thing, but 5 times 3 and 3 times 5. So 5 times 3 gives me 15. And 3 times 5 gives me 15. So that's how I get these first two in this column. Now I move on. So in order to get the next two in the next column, I know this sounds crazy, guys, but just stay with me. I'm going to go back up to the 7 and the 0, and I'm going to multiply by the values in this column. So I'm multiplying row by column. Are you with me? So let's do it again. 7 times negative 3 gives me that negative 21. And then 0 times 4 gives me 0. So that's going to be the value here. And then now I'm going to go down and multiply by the row 5, 3. By this column, negative 3, 4. And so what I get is 5 times negative 3 is negative 15. 3 times 4 is 12. And so I'll be adding those together, right? And then you guessed it, I'm going to move on. I'm going to take this, I'm going to look at the last column, and then I'm going to go back to the first row and then do the second row again, right? So 7 times 7 is 42. 0 times negative 2 is 0. So that's that element. And now I'm going to go back and do the last row over here. Trying to stick with my highlights. Y'all with me. Okay, so 5 times 6 is 30. And then 3 times negative 2 is going to give me a negative 6. And so now the result, I'm going to rewrite this. And I get 21, negative 21, 42, 30, negative 3, and what's that? 24. And so this would be the resulting matrix after doing matrix multiplication. And as I said before, this would not be the same value if for the problem part A, we were doing B times A, we would get something different. And you can kind of see why. In fact, I don't think we can do that, right? So this is an n by n matrix, and this is a row, 2 rows by 3. So this is a 2 by 2. And this is a 2 by 3. And remember, we needed to make sure that these guys were the same when multiplying. If I were to switch it around, I would then be trying to multiply a 2 by 3 times a 2 by 2, and you would see that these guys are not the same. All right, I hope that's not too complicated. I know I'm kind of fumbling around, but just stay with me. It'll make sense. So if we're taking a look at this next product, BC, we've got a 2 by 3 times a 2 by 3. They're the same size matrix, but that's not what we need when multiplying. We need to make sure that the columns of the first one is equal to the rows of the second one. And since that's not the case here, there is no product here. We cannot do it. So I hope that made sense. I know we had a couple stutter stops there. Hopefully everything is cool. Let me know if you have any questions. And I do look forward to talking to you soon. Take care.